So we did this problem in class, but I'm going to go through it step by step so that you guys, if you need another exposure to it and you need to kind of slow the explanation down, feel free to do so. I'm going to go through the electric field quickly, which is part A, and that's because we've done this before. This is from the previous unit on finding the electric field of charged objects using Gauss's law. But what we did learn is that the electric field in conductors, which is between B and C right here, and when R is less than A, we always have an electric field of 0. So you don't have to do any work there. But when we have an electric field outside of a conductor, I'm going to do when R is greater than C first, because that would be a Gaussian surface out here. And when we are outside of a circle of charge, even if there are 2 circles of charge inside, we can still treat it as a point charge. So the electric field here would be K total Q, which is our Q enclosed, over epsilon naught, which is K times 2Q over R squared, or 2KQ over R squared. So they mean the same thing, just this is the convention is to put the number in front. And then when we have an electric field here, when we identify the electric field of that one, we can still use the same equation, but we have only one positive Q enclosed rather than 2 positive Q's in the very outside. So in that scenario, we've got K positive Q over R squared. So hopefully that is not difficult. We covered that in the previous unit. These are spheres and they're conductors, so this is as easy as it gets in terms of Gauss's law. But if you are having trouble getting these equations for electric fields, please come and see me for help. Okay, now we're going to graph these, and the way you graph them is first, you know that you've got a 0 electric field between A and 0 and between B and C. And we know that we've got an electric field of KQ over R squared, which approaches 0 as the field goes out. So I'm going to make it approach 0. And same here. And then when we think about when R is greater than C and we compare the KQ to 2KQ, we know that that's going to be a larger electric field by double. And so I'm going to just eyeball and sketch the graph. It's still going to approach 0 as it goes out to infinity, but I want to show that this is double the original. Okay, now we're going to derive an expression for the electric potential as a function of distance at C, B, and A. And I'm going to do the work up here in this area because that's where we have space. And I also want to kind of keep it near our area where we have our electric field, because I'm going to need those values to do this calculation. So first thing, I don't want my thickness to be that big because I'm going to have to write small. I am going to find the potential at C, and we always want to work from outside in. We know that at infinity our potential is equal to 0, and they actually emphasize that here because we always start at 0 potential and we move our way into higher potential, which is a positive unit of charge moving into a positive electric field or a negative electric field, but we always start at 0, which is at infinity. For this scenario, we're going to use the equation, the change in V is equal to negative integral E dr. And because we have different electric fields, and even the 0 electric field is different, we have to use a different integral every time we move into a different electric field. So our first scenario is I'm trying to find the potential at C, which means I have to come from infinity to C to get that change in potential. So change in potential from infinity to C is V final minus V initial. And when I say V, I don't mean velocity, I mean voltage or potential, is equal to the negative integral from infinity to C of the electric field in that area. And the electric field in that area is the electric field when R is greater than C. So it's 2kq over R squared dr. And always remember that you can turn this into R to the negative power to make it easier. I'm hoping that this integral is easy for you and we did it in class. But if I pull out my constants and R to the negative 2, if I decrease that power by 1 and divide by negative 1, I get negative 1 over R, or I get negative R to the negative 1. And then I have to take my limits and subtract that from each other. First thing I'm going to do, I'm going to get rid of the negative. And some students couldn't figure out where the negative went when we get our potential, especially when we use our potential equation KQ over R squared, or KQ over R. But in this scenario, you can see that when you take the integral of 1 over R squared, it becomes a negative, which then gets rid of the negative in front. So in this scenario, we've got VC minus V infinity is equal to 2kq over A minus 2kq over infinity. We know that as the denominator approaches infinity, that goes to 0. And we also know that the potential at infinity, because it told us down here, is also at 0. So my potential at C is equal to 2kq. And I don't know why I put A there, but let me change that. It should be C over C. And I know you can do this equation using the potential of a point charge. It's it's KQ over R, and Q enclosed is 2Q. But I did want to show you that this is exactly what we expected. If we're outside of a circle of charge, even though it has an inner circle and an outer circle that's charged, you can just use the equation for potential of a point charge, which is KQ over R. And in this case, at the point C, we've got 2Q enclosed, and it's over a distance of C. So this is exactly what we expected for VC, and we are going to solve for VB now. Change in potential always has to represent a change in position. So this is going to be my change in potential from C to B, and that is potential final minus potential initial. And that is the integral, or negative integral, from C to B of the electric field within that region. And within that region, that's here, it's inside the conductor, the electric field is 0, which means that this expression is equal to 0. Does that mean VB is equal to 0? No, because we still have to plug in our VC expression. VB is equal to VC, which is 2kq over C. Now, a lot of students are confused by this because they see that an electric field equals 0, which means that the potential, right off the bat, they want to say the potential is 0. But it's not the potential that's 0, it's the change in potential that's 0, which basically means there's no change. So if we started off at VC on the surface of that outer shell, then within the conductor, it's going to stay the same because the change in potential is 0, given that the electric field is 0. So that's a common error that pops up with students. Okay, now when we get to VA, again, delta V is equal to VA, a lot of students think, oh, if VC was 2kq over C, isn't VA KQ over A? It doesn't work like that. And the reason why is because when we have a positive point charge on the outside that's moving in, even if we are moving into A, we have to go through electric field in this region. we have to, well, there's no electric field in this region, but we still have to account for that, which was this equation right here. And then we have to go through another electric field in this region. We actually go through 3 different electric fields to get to position A. And we need to consider all of those electric fields to get that positive point charge in. So we have to do the full integral. In this scenario, we go from VB to VA, which is V final minus V initial. We take the negative integral from B to A of the new electric field between B and A, and that's KQ over R squared dr. And then we are going to integrate this the way we did the last time. And that gave me negative 1 over R from B to A. And we're going to plug in our values. These turn into positives. I get KQ over A minus KQ over B. Now, a lot of students want to say, okay, that's my final answer. And it's actually not. The reason why is because this is still equal to VA minus VB. I need to plug in VB here to KQ over C to solve for VA. So VA is actually KQ over A minus KQ over B plus 2KQ over C. And that is the final potential at C. It's not pretty, but it accounts for all the different electric fields that this charge has to go through. Are there, if you have any questions, go ahead and email me or see me in class. Okay, now we need to draw the potential. Now, what we know about potential is that it's an inverse proportion, not inverse square, but it still looks very similar to the inverse square proportion. And we know that within a conductor, the electric field is constant. Now, this is the electric field at, not C, I don't know why my brain isn't working today. This is the electric potential at A, and we don't really know where that lies, but we know it's a constant value anywhere within that conductor. So I'm just going to draw a constant electric potential in the conductor between negative A and A. What I do know is that in the space between A and B, we've got a change in potential. And the change in potential between those 2 points is going to decrease by an inverse proportion. And then again, I have a constant because we're now in the conductor again, and that's the constant of 2KQ over C. And if you compare 2KQ over C, you can see right here that it's part of this expression and that VA has to have a larger potential. And then once you get beyond C, we get a pretty good idea that it is going to approach infinity up to that point. So this is your potential graph. Again, anytime your electric field is 0, you should have a constant between those 2 points, and then everything else would represent an inverse proportion.